Hello everyone, this is Nikhil. I'll discuss a paper on branch prediction using Perceptron. So let's start with branch prediction. Branch prediction is a method of resolving a branch hazard. It predicts whether the branch is taken or not taken. If it correctly predicts the outcome of a branch, then there will be no loss in execution cycles. In case of a wrong prediction, a stall is introduced into the pipeline. So as pipelines deepens, the number of instructions per cycle also increases and the penalty of misprediction increases. So we require a more accurate branch predictor. Here comes the role of a perceptron. What is a perceptron? A perceptron is a learning device that takes a set of inputs and combines them with a set of weights, like coefficients. You multiply this coefficient with the set of inputs and you get an output. Depends upon the output value, you classify them into different classes. So in our case, in our predictor, the inputs to our perceptions are bipolar, that is either 1 or minus 1. And the total input set of the perceptrons is nothing but an history register, where history register stores the previous branch values, whether it is taken or not taken. So the basically inputs of the perceptron are the history register. Each weight represents the degree of correlation between the behavior of past branch and the behavior of the branch being predicted. Positive weights represent positive correlation, negative weights represent negative correlation. To make a prediction, each weight contributes in proportion to its magnitude. If the resulting sum is positive, we predict it as taken, otherwise not taken. The perceptrons are trained by an algorithm that increments a weight when the branch outcome agrees with the weight's correlation and decrements the weight otherwise. So basically in this example, the branch predictor predicts taken and the actual output is also taken. Then the weight of the branch whose input is 1 is increased and the weight of the branch whose input is minus 1 is decreased. Because intuitively the weight of the branch is increased whose input is correlated with the output. And similarly, in the other case, if the branch predictor predicts taken, but if the actual output is not taken, then we'll increase the weight of the branch whose input is negative 1 and will decrease the weight of the branch whose input is positive 1. We store different perceptron weights in a table, and these perceptron tables are stored in a fast SRAM. When the processor encounters a branch in the first stage, the following steps are conceptually taken. In the first step, the branch address is hashed to produce an index into the table of perceptrons, and from the hash we pick some perceptron, let's say 8th perceptron. The 8th perceptron is fetched from the table into a vector register which contains the weights of the selected perceptron, and the value y is computed as a dot product of the selected perceptron and the global history register. The branch is predicted not taken when y is negative or taken otherwise. Once the actual output of the branch becomes known, the training algorithm uses this outcome and the value of y to update the weights of in P. So basically the selected perceptron rate is written back into the ith entry of the table. It may appear that the prediction is slow because many computations and SRAM transactions takes place, but however, a number of arithmetic and microarchitectural tricks enable a prediction in single cycle even for long history lengths. In the design space, the perceptron predictor can use both purely global history as well as a combination of global and per branch history. So, in computing the perceptron at circuit level, the perceptron output circuit accepts input signals from the weights array, which are stored in the history register, and these weights are bitwise exclusively odd with the corresponding bits of the history register. So basically, since the inputs are 1s and minus 1, we did not multiply, we need to just add and subtract the respective weights. And this addition and the sum is found using Wallace tree of 3 to 2 carry-save adders. What Wallace tree carry-save adder does is, it reduces the problem of finding sum of n numbers to problem of finding sum of two numbers. And the final sum of two numbers is carried out with a carry look ahead adder. A potential problem with any complex predictor is delay. A solution is to use an overriding predictor. In an overriding predictor, a prediction is initiated by both a quick first level predictor and a more complex second level predictor at the same time. The first level predictor gets an immediate prediction when the second level predictor can later override. So if the quick prediction is overridden, the actions taken by the fetch engine are rolled back and restarted with a new prediction, incurring a very small penalty. In this paper, they evaluated an overriding perceptron predictor in which the second level perceptron predictor is combined with the first level G-share predictor. And the results are calculated using 4K hardware budget, and a simple version of this method that uses only global history achieves a misprediction rate of 4.6% and an improvement of 26% over G-share. If we add local history to this predictor, it improves 14% over McFarlane style hybrid predictor, which also uses both global and local history. And if we add overridden perceptron predictor, then it improves 15.8% over G-share and 5.7% over McFarlane hybrid predictor.